Thanks for joining us here today at the Battle Creek Area Math and Science Center. I'm John Burdett, and I am going to go ahead and start this video with a little bit different setup than before. Today what we're going to be doing is taking that laser, shooting on that far wall, and we're going to pass in front of it what we call a diffraction grating, which is nothing more than two narrow slits in a small piece of glass. So this is a black piece with two narrow slits. So if I put it in front of the camera over here, you might be able to see the slits inside of them. So these two are side by side, and then this one is a singular. So the question becomes, if we take that laser shooting a singular beam of light, and we put the diffraction grating in front of it with two slits, what's going to happen? What are we going to then see on the wall? Will it be one line still, like one little beam like it is now? Are we going to see two? Or is something else going to happen? I want you to go ahead and pause this video and take a moment to think to yourself, and then think, which is it going to be? Is nothing going to change? Is it going to be two? Or is something completely different going to happen? And then go ahead and watch the rest of this video. I'll see you after you're done thinking. Okay, so here we are with a laser on the wall. It is an unaltered beam right now, a singular dot on the wall reflecting into the camera. I'm now going to pass in front the double slit on the diffraction grating to see what happens. Did you think there was going to be a single dot remaining, two dots, or was something else completely different going to happen? Let's find out the answer. And here we have it. So this is a single beam from a laser passing through a double slit, a diffraction grating. Only two slits. Take a look at the wall. Do you see two dots? I don't. I see a lot of dots. I see them spreading out in both directions. And in fact, I see one central dot that is the brightest, where there was supposed to be no light whatsoever, and in fact, there wasn't. So how do we explain this incredible phenomenon? We're going to need to look at some more information to find out. Wow, what a strange behavior by that light there. Was that what you expected, or was it something different? That might be one of those examples where we had like phenomena earlier. We talked about rainbows. And a test question might come up with, there's this new strange behavior, maybe even perhaps similar to the one we had there. How does that then get explained? And you need to be able to explain the underlying principles of why that just happened. But I bet you can't explain it yet. So let's get after it. Let's figure out why this really happened. We got to get to what is light itself. So one thought a long time ago was that light was made of particles, that there were discrete little chunks of light coming out of any sort of light bulb or light source, like little bubbles of light. And that would kind of make sense because everything around us is made of particles, like raindrops are particles, and yet they can form this kind of a cloud shape overall. I mean, we're made of particles, little clumps of matter. You get down to the atomic level of things. But the problem is that particles can't occupy the same space at the same time. So we get collisions. They bounce off each other. They change the course of events as things collide together. But what if, instead of thinking of it like particles, what if we thought of light as a wave? I know we've said this a few times now. But what do waves do when they collide? What if we take two beams of light and then cross them with each other? Do they bounce off each other? Do they slow each other down? Do they like mix and become one solid beam of light? Like if you took like two clumps of clay and then smacked them together? Is that what would happen with light? Well, right now there's lots of different light bulbs around me, and I'm not so convinced they're bouncing off each other. So let's take a look at a demonstration right now about water waves, where we're going to look at a water table and we're going to see what happens when the waves move on by. So come on with me. Hey guys, so I'm here in Mr. Hansen's laboratory setting. He's got a wave table for us. And so what we're going to look at is what happens if we take an oscillator, that is to say something pumping in energy into the wavetable water, and then run it by some blocks. So I've set it up so it's got two slits hanging out, and we're going to see what happens with the shadow that gets cast on the paper down here. We're going to take a look at a super slow-mo version in just a second. All right, we've changed from a double slit back to a single slit now. So we've got some cubes on here, and they're arranged so there's only one place to pass through. So we're going to take a look. If we had particles, we would expect them to go in a straight line. So only one line of things going through, like people or bowling balls. But let's see what happens when waves pass through. Thanks for joining me on that adventure over to the water table, and hopefully you got to see some of the observations right there on camera. So let's summarize those ones. When waves collide, are they going to bounce off each other? No. In fact, at the moment where they interact with each other, they appear to combine like in the animation seen over here on the right side of the screen. But afterward, they go back just as they were before. There is no height change in the small one and no height change in the large one. They move on just like they were before. So there's temporary changes, but no lasting effects. They're not permanent. So in the animation here, you notice the frequency is not changing, the amplitude does not change, but at the moment they collide, there is a temporary alteration in the wave itself. So only at that point of collision is there any sort of change, but it is only temporary. You would never know after the collision that that wave ever was in any other collision. Nothing has changed about it. So let's take a look now if we pass water waves through the two slits. I know we tried to see it on the water table before, but there's this great video here by Veritasium that we can enjoy. I'm going to put the link in the description below, but I'm going to give you a little sample clip right now to show you what he's doing with the water waves.
If light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
Where do we go from here? Look. Putting it all together, we saw with a laser that when you pass the laser through two slits, you ended up not with two lines, but with many lines. And so just like we saw in the water table, and just like we saw in the Veritasium video, that is being caused by the singular laser beam being split into two and then interacting with itself, causing the bright spots and the dark spots on the surface. So the places where we had the brightest spots, in fact, in the middle of those two lines, we had the bright spots are where we call it constructive interference. That the diffraction caused places to line up such that we had crest and crest making a supercrest, and other places where crest and trough canceled each other out. And so those would be the dark spots. And so we had bright and dark and bright and dark and bright and dark moving along instead of just two lines or just two dots, because of the diffraction and the interference of what happens when two waves collide. So when you answer a question on, let's say, a test or something like that, then you got to be able to not only just say cause interference or cause diffraction, you got to be able to articulate what's going on and causing that effect. That the interference causes the bright spots and dark spots, yes, But the diffraction is what allows one beam to be split into two and then causes the cross sections of them all. You got to be able to articulate, not just regurgitate words, but articulate what is going on. So what I want you to do is take away from this, finally connect the dots with your technology. How does this affect the technology you've been studying and working on and prepping your presentations for? What happens when two waves of your technology interact with each other? Do we get the same pattern? Does that pattern then cause something to happen inside of your technology? Spoiler alert, for some of you, yes, and for others, no, because of how your light is being manipulated. So you have to be careful in making sure, does this apply to me? Because for some of you, it does. So, my mighty rising phoenix, with your presentations just about to get ready and we're about to fire up and go, I need you to keep learning, keep earning, and as always, keep rising. Thanks so much for joining us today. I'll see you next time.